Hello, my name is Bob D. Hilster, and I am your particle model guru. Today I'm going to deviate from the magnetics, which I'll cover next time again, and talk about the mass of the G1 particle. Now, I've stated over and over again that the G1 replaces the electron, the photon, and the graviton. When you look up in Wikipedia what the mass is of these are the values you get. The electron, 9.1 times 10 to minus 31 kilograms. Very, very small amount of mass. The photon and the graviton, these rest mass are both zero. They have zero mass when they're resting. So I don't know how they get that. Now the photon the G1 doesn't replace the photon, the nucleon does, but I'm going to concentrate on the G1. It turns out that there's a number, a ratio, between the electron and the photon. And I don't know how they come up with this, but this is kind of a magic number you'll see often, that the proton is 1,836 times larger in mass than the G1. Okay, so how do they get a number? One of the, again, this is from the Wikipedia, the electron rest mass, and they literally say the electron rest mass is in kilograms is calculated from the definition of the Rydberg constant. I'm not going to go into all this, point out that there is a formula for the Rydberg constant, and when you rearrange that formula because it contains the mass of the electron, you get these values. You got the fine structure constant, you got Planck's constant, you got another, looks like the speed of c, and you've got some uncertainty principle all thrown together. It's calculated. It's not measured in that case, although they say that the electron's relative atomic mass can be measured in a Penning trap. I looked that up, decided not, excuse me, not to go into that, but just to point that that the value is calculated. Okay, but now the particle model states, I'm going to say it right off the top, all these values are wrong because of the following. The kilogram standard does not apply to the G1, and I'm going to explain that. And there is no standard for the G1 for us to compare to. Just the kilogram standard is the standard for a unit of Newtonian mass, but these do not apply to the G1 particle. But here's a more basic question. What is mass? And to me, and this is a definition I have in my book, Gravity is Not Free, mass is a property of an object that helps describe its motion. That's a general term of mass. G1 mass, Newtonian mass, that kilogram is a mass that we use to describe the motion of what? Of the apple falling to the center of the earth and the moon orbiting the earth. Mass is not real. Mass is equal to force divided by acceleration. That's an equation, and it comes from Newton's second principle, where the force is equal to mass times acceleration. You divide that little equation by acceleration on both sides, and you can get the value of mass. If you know its force and you know its acceleration, you can get the mass of that object. Being a mathematical equation, force is not real, therefore mass is not real. Mass is a property we assign to an object to describe its motion. Now the value of mass is different. This is not the definition of mass, this is the value of mass, and it's called the kilogram standard. That's an artist's conception of what the kilogram looks like. It's a cylinder. Okay, how it's made? Well, the picture is made as a computer-generated image, but the actual material is made from an alloy of 90% platinum and 10% iridium by weight. Now, here's a little piece of almost circular logic, or maybe it is circular logic. You're going to develop a standard by which you measure all the weight of all objects, and you're going to build this standard based on weight. Okay, you're going to make. How do you know you got 90% by weight and 10% by weight when you haven't got the standard yet? Sounds circular. In any case, 90% by weight, 10% by weight of platinum and iridium, and it's machined into a right circular cylinder. Right circular cylinder is a cylinder whose height is exactly equal to the diameter, and that value is 39.17 millimeters. When it's all done, they take a Sharpie and write 1 kilogram on it. Humans assign this value. Oh, okay, they don't write 1 kilogram on it. That would destroy the standard. As little as the weight of the ink of the Sharpie pen would be, it's not good procedure to be writing on it. But the point is, humans assign this value. The value of mass is assigned value. It's not the sum of its parts. They didn't say, okay, take this many atoms and this many atoms. They didn't say that. They said 10% by weight or 90% by weight. Now, if I want to know my weight, I stand on a scale and then put enough of the 1 kilogram standard objects until the scale is balanced. By the way, my assigned value is about 75 kilograms and is based on using Newtonian gravity. The scale works on Newtonian gravity. With a particle model, that's G1 gravity. Now, Newtonian gravity, the particle model suggests that there is a particle called the G1, and this particle comes at us from all directions, setting up a G1 force field around the Earth. These G1 particles pass through the kilogram standard, and then they pass through me. Some of them interact and push the standard, and some of them interact and push me. This pushing force causes the scale to move until the force on me matches the force on the standard objects, the kilogram standards. That's how they use the kilogram standard. They use it in the presence of Newtonian gravity. So they use the G1 to measure my weight. Here's the dilemma. If you want to measure the mass of the G1 particle and you use Newtonian gravity, you are trying to measure the G1 particle using the G1 force field. That's just illogical to start with. Further, the G1 does not act gravitationally with the G1. G1s do not pass through it and interact and push another G1. They don't pass through it. They hit each other and bounce away. Now, I've covered these interactions before, but I'm going to go through it again and give you some examples of why I think this is true. G1 cannot pass through another G1 or another nucleon. Doesn't pass through either one. I'm going to give you 2 examples. Magnetic repulsion. That's what I'm going to talk about in my next video. But for the moment, if you take 2 magnets, north to north, and south and south to south, and you bring those magnets together, the G1 flow through the magnet and around the magnet is such that they come right at each other, hit, and push away. The magnetic field around a magnet is a high intensity flow of G1 particles, and they push away. Those G1 particles are virtually locked into that magnet. So they might as well be part of it, because it's the G2 force that holds them there, which is the nuclear binding force. It can certainly hold the magnet together, it can hold that field together. So when you push back on the magnetic field, you push the magnet itself. That wouldn't happen if G1 passed through G1. They bounce off of. Light, ambient light, comes from that light above that shining on my face. The light hits my face, it scatters in all directions, and the camera records the image of my face. That wouldn't happen if light, which is a stream of G1 particles with a repetitive pattern, if that stream of G1 particles could pass through the detector in that camera, you wouldn't capture the image. The G1 particles are scattering, hitting, and bouncing off of either another G1 particle or the nucleon. However, let me skip here. G1 can pass through atoms and molecules. Newtonian gravity starts with the atom. And molecules are just clusters of atoms, and the Earth and the Moon and all other larger objects are nothing more than atoms and molecules all organized one way or another. The reason the G1 can pass through is because the atom is a big circular object with a lot of space, tiny nucleus in the center, and even tinier particles orbiting in that around them in some pattern. Lots of open space, and the G1 can pass right through. G2s can pass through the G1 and the nucleon. That's a necessary requirement if the G2 particle, G2 gravity, is the force holding the atoms and molecules together. As a reminder, G1 gravity keeps the Earth together and the Moon in orbit. There's an I'm using F1 to be the net force of G1 pushing G1 particles pushing this way in this direction. There are more pushing to the left here than pushing to the right at this point, and so on. You have a net force F1, which are G1 particles coming in, holding this together. G2 gravity holds the nucleus together and keeps the G1 in orbit. The second level gravity. Okay, dual values of mass. Every object has a G1 force field and a G2 force field surrounding. As one surrounding me. You can read about the fact that even human beings have a magnetic field around it. Every object has a value of G1 mass in kilograms. I have a value of mass, 75 kilograms, based on Newtonian gravity being measured on G1 passing through me, just like they pass through the standard. Every object needs, we don't have, but every object needs a value of G2 mass, and it is not in kilogram standards. The G1 interactions are clearly different than G2 interactions. They are different interactions, functionally different. G1 particle is not the same as G2 particles, and how they interact with G1s and G2s and nucleons and the rest is different. So the mass is different. We need to know what the G2 mass is for a prism. We need to know what the G2 mass is for the magnet to help understand what's going on. Okay, measuring the mass of objects using G2 gravity. G2 mass will be, when it's done, an assigned property of an object needed to help define the motion of the G1 particle around the object. Well, the problem is we're not there yet. We need to learn more about the G2 gravity. Study the prism, study the magnet, and any other place where that that G2 force field is causing interaction of the G1. We need to find a way to devise a standard. There is no standard. And I've thought about it. It's not easy It's going to take a lot of thought, a lot of testing, which I haven't done yet, and probably won't do because I don't have the resources to do that kind of thing. We need a method to measure G2 mass of any object. Once we have a standard, we have to have a method to do that. There is much more work to do. What is the mass of the G1 particle? We don't know. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I'll explain more of the universe using the particle model. Thank you for your attention.